Good afternoon, everyone. My name is Hadi Taghavifar from Durham University. Today, we will cover the storage of hydrogen in pipelines. The agenda and content we're going to cover today is the introduction of compressed gas energy storage system. Then we'll touch on objectives and pipeline compressed hydrogen energy storage will be explained. We are doing some work on the 3D pipeline modeling and material sampling, and we also have included risk assessment in our study. Then the results will be introduced, and finally we will have summary and conclusion. So this is the general schematic of the hydrogen storage system. So when there is excess electricity, the gas is going to be compressed in the pipeline. The pipeline is offshore pipeline under the seabed. And when there is need for electricity, this compressed gas is going to be expanded and go through the blades of turbine, and electricity is going to be generated by generator, and then the electricity is going to join back to the grid. This project has two main features. First, we're using the decommissioned pipelines, the already used pipelines for gas and oil. So we have to consider this fact that we are using the decommissioned pipelines. The second feature is that we're using hydrogen instead of air. So the whole feature and performance of the system is going to be affected by this fact. Our objective is to analyze the model from numerically or CFD analysis, and we have to produce a 3D model of the pipeline where hydrogen is stored in these pipelines. And our second objective is the test sampling, because we're using hydrogen, and hydrogen with steel or any other material has some different interaction compared to air with pipeline. So testing the sample tests are very important in this project. Hydrogen is ultimately is very diffusive gas with low molar mass and low density. So we have to be careful about this this fact, and we have to analyze the test samples in this project. The third item that it is within the work package we're working at Durham University, it's the thermofluid modeling of both compression train and expansion train of the system. And finally, we have to calculate the round-trip efficiency of the system operating with hydrogen in the system. Techno-economic modeling is very important, especially the pipeline is very important. When we're talking about decommissioned pipelines, of course, the capital cost for purchasing these pipelines is lower than the new one. But on the other side, we need constant maintenance, so it increases the operational and maintenance cost, or OPEX costs. So these factors have to be included in our analysis. And finally, the case studies and risk analysis and ranking of different parameters have to, we are considering these risk analysis in our study. This is a schematic of the both compression with compressors, where we compress hydrogen in hydrogen tank, and then we decompress or expand hydrogen either through the turbo expander or by combustion. Combustion of hydrogen, it's a bit tricky here because we're producing a high amount of energy and high temperature, and the blades of turbines have a threshold of tolerance of temperature. So we have to be careful about combusting hydrogen. One solution that we came up in this project is the combination of both turbo expander and the combustion of hydrogen in this system. And also, we are using thermal energy storage system as a way to increase the round trip efficiency of the system. As I mentioned, hydrogen is a very diffusive gas. So if we are considering 3% per hour leakage of hydrogen in the pipeline, I think this is normal, or we can consider the extreme condition of hydrogen leakage for this investigation. Also, when we are going to combust hydrogen, we can use equivalence ratio controller, which controls and manages the ratio of hydrogen with air, because we are trying to use as low hydrogen as possible in the system. If we are using less hydrogen, so the efficiency of the system is going to be increased. This ER controller has been integrated to the one-dimensional modeling in the Simulink procedure. So this work package of three-dimensional modeling of the pipeline and sample testing is performing under work package 2 and I think 5 from the Teesside University. This is the initial pipe modeling. As you can see, we have used the structured mesh with low number of cells for now, but in the later stage we're using the refined mesh with higher cell number, and also we are going to apply different boundary condition, initial condition to the system, and survey the more complex and sophisticated condition. This modeling in the CFD platform considers 2-meter pipeline, and also this is going to be done with the ANSYS CFD simulation software. For the sampling, 6 samples have been prepared with the dimension provided here, 1 multiplied by 1 centimeters, and the strength of these pipes are X60, X70, and X100. X100 still is going to be used for the harsh condition, long distance of pipelines. But when we are talking about X60, this can be used for onshore situation, and I think in this condition we can save money. The techno-economic analysis is in our favor when we are using X60. Also, the operational condition is under the temperature of ambient condition and the pressure of 50 bar. And the characterization is going to be done with the SEM, EDX, and XRD, which is the X-ray image processing to detect the micro cracks and the corrosion. If there is any micro cracks on the surface of the pipeline, with this measuring system we can detect in the pipeline. There has been a risk assessment. The risk factors have been identified and shared with the project members to rank the items affecting the performance of the system. The hydrogen embrittlement, depth of pipeline, hydrogen leakage, energy loss, and material fatigue have been identified and proposed for the ranking, and the hydrogen embrittlement has been identified as the most critical item with the highest impact on the risk and safety analysis. We have considered different leakage of hydrogen in the pipeline. And as you can see, if the hydrogen loss is going to be increased for 2%, then the hydrogen tank pressure is going to be decreased. And if the hydrogen tank pressure is decreasing, then the combustion is going to be diluted, and we have lower efficiency of the system, especially on the expansion train. What's interesting is that when we are using air in the system, the efficiency of the system it's around 60%. But when we're using hydrogen in the system, it's around 46. So we have to find some way to increase the efficiency of the system with hydrogen. The reason is that for compressing hydrogen, we need more power, and hydrogen is diffusive, so storing hydrogen and keeping hydrogen in tank, it requires more energy, and that's why the efficiency of the system with hydrogen is lower. But what we're trying to do, and we have done some, we took some action to increase the efficiency of the system, like integrating the thermal energy storage, and also we are using the equivalence ratio controller to control the flow of hydrogen to the system. By applying these actions, we increase the system efficiency to around 55. So this is kind of comparable with energy storage system. We haven't stopped yet there. We are pushing the boundaries forward to increase the efficiency of the system. For now, we're checking the equivalence ratio controller, and we are also integrating the thermal energy storage system to recover the heat from the combustion and take this back and recuperate this to the system and increase the system efficiency even higher than 55%. This is the preliminary result from the three-dimensional modeling. This is not final results yet, but as you can see here, we obtained some basic understanding of hydrogen storage in pipeline. Due to the law of non-slip condition, the hydrogen velocity on the border, on the outer layer of the pipeline, it's close to zero, but in the center we have the higher hydrogen velocity, and we have, of course, higher hydrogen pressure in the center of the pipe. So if we want to summarize our achievements up to now, we can say that under the same operational condition, air energy storage system has higher efficiency, but we're taking a route which leads to higher efficiency with hydrogen. Increasing the tank pressure leads to reduced efficiency, because if we increase the pressure in the tank, this requires higher energy and power from compressor to compress hydrogen into the tank. Hydrogen embrittlement is ranked as the first item with the highest impact on the safety and risk analysis. But this is among the expert views of the project member. If we take this survey to other community like industrial clusters, then we might get some other results. For the future work, we are trying to get the cost breakdown of the whole system, from compressor to pumps, heat exchangers, and everything. But most importantly, as I mentioned, the hydrogen tank or the hydrogen pipeline in the decommissioned state. This is very important. So I think this is the key point here to understand the mechanism of the decommissioned pipeline here. And also, we are continuing with the HSLA steel sample testing. This is going to be done at Teesside University. HSLA, if I think it's a high steel, low alloy steel sample that we are testing these materials. Thank you very much for your attention. That's from my side. I welcome any questions.
Yes, thank you for that good presentation. I think the concept you've been exploring is line stuffing. I think there's quite a bit of experience already on this, not necessarily with hydrogen. Did you do any studies on or work on how you might reduce a loss of 3% per hour? Because that is substantial, isn't it? And there are ways you can reduce it. Is there anything you can do immediately to, say, a factor of 10 to reduce that?
Yeah, as I mentioned, 3% is a high extreme condition we're considering for now. We can decrease it, and then when we decrease the leakage of hydrogen, of course, the efficiency of the system is going to increase. Back to your question, I think when you were saying that what are the solutions to decrease this one, I think this goes back to the material side, and we have to find some way to upgrade the steel or material performance to decrease the embrittlement of the steel, or this is the first thing that comes to mind. I don't know, Andy, you think there's any other solution to decrease the leakage? Because this is the key.
From joints, not from the steel, I assume. It's not from the steel, it's from the joints.
Yeah, we're getting some feedback from our industrial partners, Crandall Energy. Actually, they're giving us consultation regarding the fixtures and welding of joints. This is a 25-kilometer pipeline, so we need to have a seamless pipeline infrastructure to decrease the leakage of hydrogen. But regardless, whatever we do, I think hydrogen is very highly diffusive, and controlling hydrogen is a tricky task. Yeah, sure.
Eddie Holstead from the Environment Agency. Just thinking about the transferability of the research, because you're looking at hydrogen in pipe, and I guess one of the assets Tees Valley has is the salt caverns. So is that a separate kind of case completely, or are there kind of things that can be learned from this that might be applicable to those?
Yeah, these are kind of alternatives for hydrogen storage. For this system, metal hydride compressor is also introduced, that instead of pipelines, we can use the metal hydride to compress hydrogen gas into the solid state and store hydrogen in this device and in this tube. The salt caverns or other technologies are out there, and there's possibility to define some projects and investigate the feasibility of such a hydrogen storage scheme.
So the salt caverns, this has been studied quite a bit. Over the years, we wanted to do something different, and we wanted to focus on offshore and onshore pipeline assets, which may well be decommissioned. So what's an alternative to oil and gas for those assets? So that was the focus, to take that different. May not be where you want to put it ideally. You ideally want a new build system, but actually recognising there's already stuff there. What could we utilise it for into the medium term without scrapping the whole thing?
Yeah, it's a dog win with Pensad. We had a chat before, and very interesting presentation. But the fatigue analysis, did you consider a pre-existing planar floor, or do you think there could be with the pipeline? Because a lot of the work that we do with pipeline operators, the fatigue looks good on an SMN case where you consider there's no imperfections, but once you start considering the imperfections could behave like a crack and the fatigue, then that's when things get a bit more interesting. So I was wondering if you did that and whether that's in your consideration if it works.
The main challenge here is the cyclic pressure of hydrogen, internal pressure from the inside pipeline with gas, hydrogen gas, and in the outer layer we have the hydrostatic pressure from the sea. So these pipelines are going through two hydrogen pressure, outer layer and inner layer. So fatigue and crack studies are very important, and especially particularly for the decommissioned pipelines, that this increases the chance and probability of fatigue and crack detection on the surface of pipeline. For now, I think the progress is undergoing at Teesside University. There are some devices to test the samples. Usman, if there's anything regarding the progress, can you share?
We are doing some experimentation with different type of materials, like 60, 70, 600, at 50 watt, the capacity we have at the Teesside, and we are examining a different cycle of times. In addition, we are trying to do some CFD analysis, in which for our 2 meter pipeline, which we have indicated just the basic runs we have done at the moment, and we have planned to go for fatigue and other material analysis through CFD or ANSYS.
Because having looked at a lot of pipelines worldwide, the issue that we're coming across when we're repurposing gas pipelines to hydrogen is you may have a small imperfection in the long run, in particular from the manufacturing process, which would have passed out from the mill, they would have passed the QAQC, and they can grow under fatigue in oil operation or gas operations. And when you model that in hydrogen, a pre-existing defect, that's when you can get lower fatigue lives. So it's that, if you have good inspection technology which gives you a pipeline a good clean bill of health, then you don't have to consider that. But doing the fracture mechanics on that is where we do a lot of our work of operating.
I think one of the good solutions is also using FSI, fluid solid interaction with softwares, where these softwares can be tested in different boundary conditions. The corrosion on the surface and material can be applied in these CFX kind of simulation of pipelines with hydrogen gas. These are all part of the work packages and deliverables that we have to study and investigate in depth during our project.
Great. Well, thanks very much for the presentations and obviously for everybody